My name is Vahid Hashemian, a staff software engineer at Pinterest and a Kafka committer and a PMC member. Unfortunately, my co-speaker Jeff couldn't make it to the conference, but he made great contribution to the content that I'm presenting today. So I hope that I can do a good job covering for him. I'm going to start with a little bit about Pinterest and the PubSub ecosystem, and then move on to the work that we have done over the past few years, I would say, around consolidation, automation, and scalability and efficiency of the platform. And then I'll wrap it up at the end with the key takeaways. Pinterest is a visual discovery platform, as you probably know. It's built on top of three main pillars of search, social, and commerce. And the mission of the company is to bring everyone the inspiration to create a life they love. In terms of services, there are 300 plus services running on thousands of EC2 instances. And majority of these services run on open source software. That's either software that we borrowed from the community or adopted from the community, or software that we internally developed and open sourced. Looking at the numbers, if you compare the more recent stats compared to where they were a few years back, you can imagine the challenge of each of the engineering teams in terms of how to cope with the scale of the company. And the PubSub platform is not an exception to that. So the PubSub platform has a very standard high-level architecture and ecosystem. We have systems that gather data from the app and the web interface and use producers that directly interact with the PubSub layer. And on the other hand, we have systems that extract that data for various use cases, and they use consumers that, again, directly talk to the PubSub layer. More concretely, this was our ecosystem a few years back. We had applications, standalone or streaming applications that used native Kafka clients to talk to Apache Kafka to produce data. We had several services that used our logging agent called Singer, which is deployed on every single host at Pinterest. Basically, those services log to disk, and Singer will ship the content to Kafka. We also ship MySQL change data logs through Maxwell to Kafka. And at the downstream side, again, we had applications that use native Kafka clients to ingest and process that data from Kafka. And we also had applications, analytic applications, and query engines that use the S3 dump of the data to run the business logic. So now let's move on to the work that we have done. So there are three main areas: consolidation, automation, scalability, and efficiency. And majority of this content we already presented at Kafka Summit in London in March. So I'm going to talk a little bit more fast on those sections. I still try to give you the context, but in case you are interested, you can refer to that talk. And I also have QR codes and several slides that point to blogs that explain those items in details. So that's the reason for doing that is that I have some new contents that I want to spend more time on towards the end. So you see the slides that have that recap icon at the top right. Those are the ones that have been presented before. So in terms of consolidation, we had, back in the days, we had client libraries, various client libraries, different languages, different versions, talking to Kafka. But the platform team didn't have any control over those libraries. Developers use whatever version of the library they wanted. And because they didn't have detailed knowledge of the PubSub layer, they had confusion or lack of knowledge around how to discover the Kafka cluster that they need to talk to, or how they can optimize the configuration of their clients. And we had issues also as well on when there were bugs in the client library, and we were seeing growing number of those, where the bug in the client library bubbled up to the application and kind of interrupted the application, causing downtime. And that took significant time from not only the application developers and the service team, but also from the platform team. So when we thought about that, we realized that the main challenge, the main issue is that the tight coupling between the applications and the Kafka clients, or the Kafka as a platform. And the solution we came up with was to create a layer between the application and the PubSub platform, or PubSub layer, to not only kind of hide some of the complexities of the PubSub, but also work as a defense mechanism against bugs and things like that. So this library is called PubSub Client, or PSC, that runs a single certified client library version under the hood. It provides several features to users, and I'll talk about some of those a bit later, like cluster endpoint discovery, optimized configurations, and it also kind of make the bugs in the client library, at least the ones that are auto-recoverable, abstract to applications. It also provides pluggable interfaces that users can adopt and customize, like they can create their own producers and consumer interceptors. And we also made it Flink friendly by creating the connector for Apache Flink as well. This library has been running, the Java version of this has been running in our production since 2 years ago. So we added PSC to this ecosystem and started deprecating the direct use of native Kafka clients. The other area we spent time on was storage CDC. You saw in the earlier chart that we used Maxwell to kind of ship MySQL bin logs to Kafka, but we had other storage solutions or storage systems at Pinterest that started to need the same CDC pipelines. For example, HBase, KVS store, and things like that. But we realized that we cannot have every kind of a storage system have its own CDC solution, because first of all, it's hard to maintain. And the second is, if the storage is going to be replaced at some point in time with another one, we cannot kind of throw away the old CDC solution and create a new one. So that's why we went with generic CDC built on top of Debezium to provide a unified solution for all the storage CDC at Pinterest. So we replaced, improved that and consolidated the CDC layer as well. Moving on to automation. So with automation, as you saw, we have growing number of use cases, growing number of users, and all of that means that there are more traffic coming to the PubSub clusters, and more topics are created, more pipelines are created. And managing that is not going to be a manual operation. The other solution, or the other product that we created, was called Orion, which is an automated distributed cluster management. And we onboarded Kafka as the first implementation of that, which to manage Kafka clusters. Orion basically it gives the overview of the cluster in terms of the brokers, topics, partitions. And it's also a primary on-caller for us for simple recovery operations. For example, if an EC2 instance goes bad, Orion handles the broker replacement for us without even getting the on-caller notified. And also gets rid of all the error-prone, repetitive, time-consuming tasks that we used to do, and they were mostly not auditable. Orion comes with three main type of components: sensors that basically collect data from the Kafka clusters, topics, brokers, partitions. There are operators that they do the kind of automated actions. For example, if there is a topic configuration update, that Orion handles that. If there are assignments or rebalancing of partitions, again, Orion handles that. And there are actions for admin users. For example, whenever we want to roll in, we start the cluster, or we want to launch brokers or decommission brokers. Again, there are actions are there for the admin user. These are a few views of Orion. This is the topics view in like shopping Kafka O1 cluster. You see the list of topics, partitions, and information about those. And then when user clicks on a topic, they see the list of partition and their placements. List of brokers. These are the status of the operators and sensors, and also the actions that Orion has taken, the history of actions. Moving on to some of the challenges that I earlier talked about in terms of client libraries. I mentioned that there were challenges in finding the right configuration for client libraries. For example, SSL-related configuration, bootstrap servers, and also finding the right configuration for a specific configs. For example, linger.ms is by default it's set to 0, but that doesn't work well for the platform. The other challenge I mentioned was service owners having challenges with client bugs that impacted the applications. So to simplify configurations, we adopted the notion of resource names at Pinterest. And basically, when a user goes and creates a topic, they automatically get a resource name like this, and they feed that to PSC library. For example, PSC consumer says, subscribe to this resource name. And then under the hood, the library can go and does the bootstrap, find the bootstrap endpoints, and also does the override for the default configurations that work best for the platform. So with this, the developer gives developer a chance to focus more on their application logic and frees them up from setting up the consumers and producers of the PubSub layer. And in terms of auto recovery, some of the issues that we have seen is whenever there are broker replacements, we have seen that sometimes the metadata on the client side goes out of, it becomes stale and it becomes out of sync. But those are really easily fixable by just shutting down the consumer or the producer and starting a new one with the same config. So that's basically what PSC does under the hood. It basically catches those exceptions and tries to reset or retry the operation. And again, since we enabled that for the applications, we've seen huge improvement in terms of KTLO, and specifically for the Flink applications that frequently run into this issue. So scalability and efficiency. Back in the days, we used to run on homogeneous instance types. We were quite lenient on the replication factor and retention of topics. And we also were seeing growing number of use cases that sent huge throughput to the Kafka clusters. These pipelines these were usually ML training pipelines that didn't really need low latency ordering or any key partition requirements or any transactions. So looking at the Kafka clusters, we realized that, okay, each cluster has its own resource footprints. And some clusters are disk bound, some are CPU bound, and some sit somewhere in the middle. And there are instance types that fit each of those scenarios. So we went with heterogeneous instance types, depending on the cluster resource requirements. And we dropped the default replication factor and retention of topics, because for replication factor, there are a lot of topics that don't really need the availability provided by 3 replicas across 3 AZs, and 2 is good enough for them. And with time retention, because we had a more mature PubSub platform, we didn't really need to keep that much of a buffer for data on disk. We also did several computer optimizations. Those were presented last year in re:Invent. In case you're interested, you can watch that recording for details. And for those high throughput pipelines, we created MemQ. MemQ is a scalable cloud-native PubSub platform that is developed internally at Pinterest. Its development has started in 2018, and it's been running in production in the company since 2020. memqueue uses object store only. There is no local storage, which simplifies a lot of operation like scaling up or down because there is no internal state to replicate. It handles gigabyte of traffic per second, and end-to-end latency is slightly higher than Kafka, but it's still under 10 seconds. And it scales writes and reads independently. Writes are going through the memqueue brokers, but the reads are directly done on the object store. And for those type of use cases, memqueue runs 90% cheaper than Kafka for us. Side-by-side comparison of some features, memqueue runs all by default. It also has built-in data loss validation. And thanks to PSC that supports not only Kafka clients, but memqueue clients, it provides Flink support as well. But as I mentioned, there is no ordering or transaction support. In terms of numbers, on Kafka side, we run about 70 clusters, 72 million messages second at peak, and 32 gigabyte a second compressed traffic coming to the clusters. And we run about 1,800 brokers. But on memqueue side, we have 13 clusters, 28 gigabyte a second at peak, and 300 brokers. So you see that even though with memqueue we get about 75% of traffic compared to Kafka, it's running on about 15% as many brokers. And this is the breakdown of the number of brokers over time between Kafka and memqueue. And because of these optimizations that we've done, we have been on a downward trend in terms of the total number of brokers. And that's interesting because since last year, I was looking at some of the stats. We had about 20% growth in the inbound traffic to these clusters. So we added memqueue to the heart of this, in this heart of this ecosystem, and it basically has the same arrows connected to it, same with Kafka, except for CDC that is not really a good use case for memqueue. The other improvement we did was around Mirror Maker. We run Mirror Maker v1, and it's used to mirror compressed topics between regions or from prod to test and dev clusters. The challenge we had with memqueue is because it does decompression, deserialization, and then serialization and compression at mirror nodes. As traffic went up and down, we saw CPU increase and CPU spikes, and also occasionally OMs on the mirror nodes, which mainly was because of the overhead of that decompression and recompression on mirror nodes. So we created shallow mirror, KEEP 712. Unfortunately, it didn't make it to the open source because at the same time the community was moving to Mirror Maker v2. But the idea was simple. We just tried to bypass that decompression and recompression, and the way we did it was we updated the producer and consumer API protocol to work with the raw records, raw batch records. Raw record batches that is coming from the fetch response. So basically, the mirror node will call the fetch response on this new protocol and gets raw batches, raw record batches from each partition, and then regroups them and sends them through the producer to the target cluster. And you see on the metric on the right-hand side, bottom right, that after migrating to shallow mirror, basically we went from a fluctuating CPU utilization to just flattened trend. And that not only improved the stability of the mirror clusters, but also dropped the cost of running them significantly. So, so far the items that I discussed were already presented last year, and the tiered storage is something that we have been recently working on. So this is the new material that I'm hoping I can spend some more time on. So with tiered storage, the answer why we need tiered storage is pretty obvious. If you look at the cost of hosting a Kafka topic, the cost depends on several factors. The replication factor of the topic, the inbound traffic of the topic, like gigabyte per second, the retention of the topic, and also the cost of hosting the topic per gigabyte. And I mentioned earlier that we already optimized replication factor on retention. The gigabyte per second is also optimized by using compression. But so the last item to optimize is cost per gigabyte. And of course, object store is a much better or much cheaper way to go about that than the local disk. So the native implementation that is available now in the Apache Kafka open source is the same. I showed this in this diagram that is taken from an Uber article on the subject. Basically, in this implementation, broker takes the center, is the centerpiece. Basically, broker handles log segment uploads to S3 and also serves the data to consumers, whether they are on the broker or whether they are on the object store. So, but this wasn't an option for us for two reasons. First of all, we run brokers that are running older version of Kafka, and upgrade is not an easy thing to do for us. So basically, we couldn't use the offering from the upstream, at least right away. And the other reason is even with the upstream solution, since logs are served to consumers through the brokers, for consumers that are basically lagging behind or they are replaying the topic, basically they impact a lot of CPU, IO, disk IO and CPU spike on the brokers, and we really didn't want that. And we also had a proven idea from MemQ. I mentioned that in MemQ, reads are served or scaled differently than writes. And we thought, okay, we can take the same approach with consumers. So basically with this approach, local logs are served as before through the native library. Logseg brokers basically sends back the records to consumers. But for tiered storage, consumers directly talk to the object store. But for this to happen, we need a couple of things. First, we need a component on each broker that can handle the log segment uploads, because we're taking broker out of the picture for that. And we also need an extended version of Kafka client library that can serve logs from tiered storage as well. So with this solution, as I mentioned, we get the benefit of the native implementation in terms of reducing the disk requirements on each brokers, but we also get lower CPU and disk IO on the brokers because we are basically removing those backfilling and lagging consumers, which means that the broker load becomes more predictable over time, and we don't need to allocate as much buffer on the brokers in terms of CPU and disk. So which means that we can do a more aggressive bin packings on the brokers, which at the end results in fewer brokers in the cluster and reduced cost. So this is a side-by-side comparison between the native tiered storage and Pinterest tiered storage. I don't go into the details of this, but the native solution is best when we cannot go away from the native Kafka library for our applications, and we need to centrally manage authorization at the Kafka layer. But if broker upgrade is not an immediate option, or we have recurring backfilling or lagging consumers, or we really need the cost reduction is the highest priority, the Pinterest tiered storage would be a better solution. The high-level architecture is like this, pretty simple. As I mentioned, we have the segment uploader running as a sidecar, at least at Pinterest, on each broker. And then the sidecar will basically upload the rotated log segments to object store. And on the application side, application uses the tiered storage consumer, which internally relies on native Kafka consumer or an object store consumer that is coming with the library. A more detailed look at this. Producers work as before. They write to Kafka, and Kafka, again, writes incoming data to log segments under the specific path for each partition. And the segment uploader keeps watchers on Zookeeper or Kraft to be aware of metadata changes, specifically leadership changes for partitions, because the segment uploader on each broker only uploads segments from partitions that that broker leads. And that's similar to the native implementation. And then once the uploads happen, they are available for the consumer to consume. A more detailed view into the segment uploader. On the left, you see the different partitions and their log segments and index files on the broker. So those partitions that the broker leads, they can be in three different states. They can be uploaded already, they can be queued for upload, or they can be active, which means that the broker is still actively writing to them. And the segment uploader, through the watcher and Zookeeper, knows which partition it needs to kind of keep an eye for, and then it keeps file system watchers on those libraries to detect when a log segment is rotated and is available for upload. And then when that's the case, it's added to the upload queue, and in time it's sent to object store. There are retry mechanisms available in case like the initial attempt fails. And once a log segment and its index files are uploaded all, there is an offset watermark file for each partition that is updated and uploaded to object store as well. And that's mainly as a checkpoint in case there is a downtime or there is a leadership change. The next time the broker comes back up and segment uploader starts, it knows where to resume uploads from. There are a couple more components. There is a storage service at the bottom, middle bottom, a storage service endpoint provider. Basically, that's dependent on the type of object store that is in use to handle things like, okay, where the partition, the log files, or where the prefix for a given cluster's topic partition is. And there is also a Kafka environment provider for extracting things like, okay, where the Zookeeper endpoint is for the cluster. So in terms of fault tolerance, I already mentioned that the retry mechanisms or fallback mechanisms are in place for failures in upload. In terms of uploader availability, I also mentioned the offset watermark file is the checkpoint that we keep. But the other thing that is a little bit more tricky is log segment deletion on the brokers due to retention, because brokers no longer are involved in the upload. We cannot really control when the broker is going to delete a log segment. So looking at this a little bit more closely, the life cycle of a log segment is like this. Typically, the log segment, when it's created, is initially active. It's getting new messages until it reaches the size limit that is set for the topic, which is 1 GB by default. And then after that point, it gets rotated, goes to a rotated state, and it stays there for the duration of the retention, whether it's in milliseconds or in bytes. And then after that point, it goes to a stage for deletion. And it stays in that state for a configured log segment delete delay millisecond, which is a broker configuration. And after that, it basically deleted from disk. There is an exception to that, those states, and that's when the topic doesn't get a lot of traffic and its retention arrives before it reaches that 1 GB or the size limit, in which case it immediately switches from active to a stage for delete. So this is not, since this applies to topics with low throughput, these are not really ideal use cases, and they don't benefit as much with tiered storage. But this shows that the maximum time we have to upload a log segment from a broker is that configured log segment delete delay MS. And that configuration by default is set to 60 seconds. And with our environment, bumping it up to 5 minutes seems to be working well for us. So by bumping that configuration, we kind of mitigate the risk of losing data. Moving on to the consumer side, the tiered storage consumer wraps around the Kafka consumer and object store consumer, as I mentioned. So basically, when the application creates a tiered storage consumer, under the hood, the Kafka consumer and object store consumer is created. One thing we do is we rely on Kafka consumer for consumer group management and offset tracking. So when there's a subscription or assignment of partitions, basically we get that, we relay that to the Kafka consumer, and once partitions are assigned, we go to the object store consumer and set the locations that that consumer need to watch for and download and serve from. And then the seek to offset happens depending on where the offset is, and then the polling loop starts. There are 4 different consumption modes that we can support with this consumer: remote preferred, Kafka preferred, remote only, and Kafka only. For example, remote preferred means if an offset exists on object store and on Kafka, serve it from object store. And for example, Kafka only means if the offset exists, the Kafka only means only serve the offsets from Kafka. We don't care about tiered storage. And the diagram shows an example. For example, you see the red box, the offset, the log segment for offset 0 to 99 has been removed from the broker and it's available on object store. So only all the consumption mode can still consume from an offset like 20, except for Kafka only mode. And on the other extreme side, the right-hand side of log segment 400 that contains offsets from 400 to 499, in this example, only is available on broker and it hasn't been uploaded to object store. So all the consumption modes would be able to consume from offset like 455, except for remote only, in which case it goes to an offset reset. So looking at one of the options, how internally it works, Kafka preferred, the application sends a poll call to tiered storage consumer, and it relays that to the Kafka consumer because we are in Kafka preferred mode. And the poll is done against Kafka cluster. And if there are records coming back from that call, they are returned to the application, and the case is closed. But if there are exceptions saying that offset doesn't exist on the broker anymore, we do a poll call through the object store consumer to the object store. And if there are records available for that offset, the record is available, it's returned to the application. And if it's not, an offset reset happens based on the auto offset reset configuration. In terms of the cost saving, for us, considering if a topic is already on 6-hour retention, without tiered storage, and we move this to tiered storage with 1-day retention on S3 and 3-hour retention on Kafka, we see about 32% saving in cost of hosting the topic. But if we drop that retention further to 1 hour, the cost goes up to about 58%. And in terms of reduction, the reduction applies when the consumers are consuming in non-easy aware mode. And that's the difference is quite big mainly because of the difference in the cost of running traffic across AZs compared to the cost of gets to S3. So the tiered storage is the latest addition to our ecosystem. And we have an article that describes tiered storage in more details. We also open sourced it, so it's available. There is a link in that article if you're interested. And to wrap up, and the key takeaways are, and we heard that on the yesterday keynote, that data streaming should be simple. It should be simple for application developers by abstracting a lot of the complexities of systems for them. And it also should be simple for platform owners by adding to the automated operations. And I kind of explained how PSC, generic CDC, Orion are examples of that. It should also be efficient, meaning that the cost of running the platform should trend much lower than the traffic, the growth of traffic coming to the platform. That was the content I had planned to share with you. I hope you find it useful. Thank you for attending.